In this video, we're going to continue discussing section 6.1, which is talking about probability distributions and random variables. So in the last video, we finished up by looking at discrete random variables and finding probabilities about discrete random variables. We can also look at properties of that random variable or of those random variables and sort of how they behave in different ways. And so the first thing I want to talk about here is we can talk about different summaries of the distribution, but what you're going to find is weird or different from what we did the last time we talked about summaries of data or distributions, is that this time it's theoretical. So specifically what I mean is that we're going to talk about the mean and the standard deviation of a random variable. Okay, so we talked about the mean and the standard deviation of data before, and that was pretty much self-explanatory, looking at how where the center of the data was and how spread out the data was. I think that probably made sense to everyone, but here we're going to talk about the mean and standard deviation of a theoretical thing, which is much more non-standard. So, and I make an important note here that they are not about their sample counterparts. The sample counterparts are what we talked about in the first couple chapters. In this chapter, we're talking about the theoretical version, and the theoretical version means about a population, about the entire population, not just the sample that we took. Okay? So specifically, these are called population parameters. And that word parameter is going to be important. If you read the reading from last week in the Lady Tasting Tea book, they talked about parameters. And so Pearson used parameters in this manner. They are things or objects about that population. Okay, so the mean and standard deviation are called population parameters when they're of random variables. When it's of data, specifically, they're called statistics, sample statistics. Okay, we're going to denote the mean of any random variable. So whenever we're talking about the mean of a random variable, we say the Greek letter mu. Okay, so that looks like it's not an M or it's not a U, it's mu, Greek letter that looks like that, and the standard deviation is denoted as sigma. Okay, sigma, another Greek letter. It's an O with a little sort of thing on top there that goes off to the right. Okay, so mean and standard deviation is mu and sigma. Okay, the mean of a random variable mu is the theoretical average of a random phenomena. Okay, so it's the theoretical, not actual average of data, theoretical of that random phenomena. It's also called the expected value. So we can have, we can call it the mean, or we can also call it expected value. And it's denoted as a function, e, and then the argument to that function is the random variable x. So the expected value of a random variable is the theoretical mean. So we can actually calculate this by hand for a specific theoretical random variable and for discrete random variables, which we're talking about right now. Okay, and it looks like this. Okay, so e of x, okay, the expected value of the random variable x is equal to this capital sigma, also a Greek letter, which in mathematics represents the sum. Okay, so it's the sum of the observation times the probability of that observation happening. So this here is the outcome, and then this is the PMF value at that specific outcome. Okay, and then we sum over all outcomes. Okay, I know my handwriting is terrible here. Okay, so we have, you take the outcome times the PMF value at that specific outcome, and then you do that for all possible outcomes and add up those numbers. Then that's going to get you the theoretical mean or expected value of a random variable. So the standard deviation is the theoretical measurement that measures variation from the mean. So we talked a little bit about what standard deviation does before. It's harder to interpret. It basically says how spread out the data are for the sample stuff, and this is how spread out the theoretical values sort of are for the random variable. You can also calculate the standard deviation of a random variable easily, okay? And it looks like this, okay? So there's a little more added here, but it has the same basic flavor. If I take away all this previous stuff here. Okay, it has this same sort of sum here, but now the only difference is now we have x squared instead of just x. Okay, and then after we do that sum, we subtract away the mean squared. Yes, because up here, this value is that mu, that mean. Okay. So we need to find the mean first before you find the expected value. So here's an example of first setting up a PMF or a probability distribution for this situation. So we're going to approximate reality with a probability distribution. And then we're going to find the mean and the standard deviation. So this sort of encompasses all that we've done so far as a in chapter 6, section 1. Okay? So suppose that you're playing a game to possibly win some money. All right? To play the game, you must pay $3. The game consists of you picking a card at random from a standard deck of cards. If you pick an ace, you win $50, else you get nothing. Okay, so, and I tell you specifically what X is supposed to represent. It represents how much money that you walk away with after you're done playing the game. So the first thing that we need to do here is set up our distribution. So we need to set up our probability distribution. Okay, and so it starts with X, the possible values that X can take on, and then in the bottom, the probability that X equals X. Okay, so this is the PMF, and then up here, this should be, a capital X up here. These are the outcomes. So think a little bit before I tell you what the possible outcomes of the random variable are. Remember that the random variable is how much money that you walk away with. Okay, so hopefully you've thought about it for just a little bit. There are two possible outcomes here. You win or you lose. Okay, so we'll first start with losing. If we've lost the game, how much money net have you won or lost is maybe another way to say this. Okay, and it turns out that you've lost. If you lose the game, then you're sort of out $3. Yes. So if you paid $3 and then lost, you didn't get any back, but you lost $3. Okay, and then if you win, the game, you win $50, but of course you paid $3 already. So, oh, weird stuff happening here. We've got x, and then the probability that x equals x here. You lose -3, okay, or you win. And if you win, your net earnings are $47, okay, because you won $50, okay, and then $3 to pay. You paid $3 beforehand, so you walk away with essentially $47. Now comes maybe the more trickier part, is calculating the probability that each of these happen. So, for those of you who don't know, a standard deck of cards is 52 cards. Okay, there are 13. There are 4 suits, which are different kinds of cards. There are hearts, diamonds, spades, and I forget the fourth, clubs. Okay, hearts, diamonds, spades, and clubs. There's 4 suits, and there are 13 different I'll call them faces for the cards. It starts at 2. It goes from 2 to 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Then Jack, Queen, King, and Ace. Okay. So essentially, there are 4 of each face in this deck. Okay. So there are 4 aces, 4 kings, 4 queens, 4 jacks, so on and so forth. And so the probability of randomly picking an ace out of that deck is 4 out of 52, or 1 out of 13. Okay, so it's 1 out of 13 is the probability that I win, which means the probability that I lose is 48 out of 52, or 12 out of 13. Okay, sorry for my horrible 3. And so this, altogether, is my probability distribution. Okay, it lists all possible outcomes of my random variable and the probability that each outcome happens. So now I want to calculate the mean or the expected value of this random variable. And so you do that by, the formula is summing over all possible outcomes, the actual outcome value times the probability that that outcome happens. So let's do that. Okay, let's do the inside first, or we'll start with the first one. The x is -3 times the probability that x happens, 12 out of 13. Okay, plus, and that's where the sum comes in, plus the other outcome that possibly happens, 47 times 1 out of 13. Okay, and when you do that calculation, you can multiply through and get -36 over 13 plus 47 over 13. And then when you add those two together, you get 11 out of 13. Okay, if my math is correct there. This represents, or this says, this number, 11 out of 13, says that on average, you will win whatever 11 out of $13 is per game that you play. So on average, you're going to walk away with, let me calculate that here just to give you a number. 11 out of 13 is 0.846. Okay, so this, as a number, says that for every game that you play, you're going to walk away with, on average, 84.6 cents. Okay? So hopefully that makes sense. Now that's weird because you can only, you either lose 3 or you win 47. So you might say, well, what the heck? Why is this saying that every game that you play, you're going to walk away with, on average, 84 cents or 85 cents? That is the, if you think back to chapter 5, that's the theoretical long run average. So if you play this game many times, you're probably actually going to come out on top. Okay? And if you divide your total winnings by the number of games that you played, it's probably going to be somewhere close to 84 or 85 cents. Okay, that's what this is saying. Now, we can also calculate the standard deviation, which is a little bit more of a calculation, okay, but not too much. The standard deviation of a random variable looks like the sum of x squared times the probability that x is equal to x. Okay, you do all that, and then you subtract away the mean squared. Okay, now I'm writing big, so there isn't a lot of room here, but you'd have negative 3 squared times 12 out of 13 plus 47 squared times 1 out of 13. Okay, and then you do that calculation all in the parentheses, and then you'd subtract away 11 out of 13 squared. Okay, now I don't have that pre-calculated, and there's not really room here to do any sort of calculation. So in class, we'll talk about this, and I'll give you the answer there, but that is the calculation. This is the calculation that needs to happen to get that standard deviation. So hopefully that made sense how I wrote out the equations in actual numbers. Okay. So lastly here, I'll talk about continuous random variables. A continuous random variable is one that takes on possible values that form an interval. And so we talked about this before with continuous and discrete variables in general. For continuous random variables, there are theoretically an uncountably infinite number of possibilities that could happen. All right? Unlike discrete random variables, the distribution of a continuous random variable assigns probability to a range of possible values. Now, this is weird and something that you have to keep in mind. So it assigns probability to a range of possible values, not to a specific point. So in discrete world, probability only happened at a single point. Okay, that's an important phrase that you might want to write down. For continuous random variables, probability happens in an interval. And so you can use this analogy, or I'll use this analogy to try to make sense of what's happening. If I suppose that I'm running a half marathon, okay, and I ask you, that's a continuous, and so that's a continuous sort of situation, okay, depending on how precise our measurement tool is. If I say, what's the probability that I run the half marathon in 3 hours, 10 minutes, 12 seconds, 13 milliseconds, and 19 microseconds? What's the probability that I would actually run it and end on that specific time if we got really specific? The answer is probably 0. Okay, or it is 0. The probability at a specific point does not exist in the continuous world. But you could say, well, what's the probability that I run it in between 3 hours and 10 minutes and 3 hours and 20 minutes? Then there is some sort of probability associated with that. Well, maybe there's a 20% chance that I run it in between those times because I'm slow and I don't run a lot. Okay, so it's going to take me a while. So that's what I mean here in this paragraph. Very important distinction that we need to make. Okay? So it has a number of important consequences. I talked about a bunch here probably. Discrete random variables probability only happens at a specific point. Okay, the probability that x equals at specific point is equal to a. Okay, if x is not a possible outcome, then the probability that we see that is 0. For instance, if we roll a dice and I'm interested in the probability that the outcome is 3.2, that's not possible because it's only 1, 2, 3, 4, 5, or 6. Okay. For continuous random variables, probability at a point is 0. Okay, and we're actually looking for area for probability between 2 points, A and B. Okay, and this A is different from the A that I have above. Okay, just a coincidence. And how we find probabilities for continuous random variables is actually looking for the area under the curve from A to B. So all continuous probability functions are going to be represented as a curve. Okay, and to find probability, we're going to look for the area under the curve from point A to point B. So as an example, here's an IQ score example. Okay, this is a continuous random variable curve. This is in fact the most important one, the normal curve. Okay, but it looks like this. It is a curve. Okay, and so we can, in order to find probabilities about a specific situation, we're going to find the area under the curve from point A to point B, and that's going to be the probability that something happens. Continuous random variables have the same properties as discrete ones, i.e. the mean and the standard deviation, but the only difference is that instead of the sums that we used to calculate the mean and the variance, we have to use integrals. Now, this course does not require that you take calculus or you know what an integral is, so we're going to skip over that kind of stuff. Okay, and that's where we're going to end this video on. We'll finish chapter 6 and more stuff next week.